Good afternoon. I'm Malik from Adobe Research. Today I'll be talking about deep learning model performance comparison and using visualization and interaction for that. I'd like to thank my co-authors, specifically Sugeerth, who couldn't be here because of visa issues, but he did most of the work. So I don't think I have to tell anyone here that data science is a complex process with many steps, many sub-steps within each of these. So like I said, I'll be focusing on the task of model comparison specifically. And this is because in talking to machine learning experts, we found that model comparison comes up a lot, particularly in the model tuning stage, where machine learning practitioners might be tuning their parameters and trying to figure out the best combination of them. They might be comparing against previous iterations of the same model. And then finally, once they have their model in the evaluation step, they might be comparing against other people's models or the state of the art, which might have completely different architectures altogether. And beyond machine learning practitioners, there's other cases where comparison might also be useful. So for data scientists who might want to be doing some sort of training set validation, they might want to compare the same model trained on two different training sets to understand the gaps and biases in them. Or non-experts might have access to some pre-trained models and might bring their data to the model and use this for model selection. So at the core, the research question that we're looking after was how can we build visual analytics tools to help machine learning practitioners systematically understand the similarities, differences, and trade-offs between multiple complex models. Because also while talking to a lot of these machine learning experts, we found that this comparison task is done a lot based on intuition of how to proceed or using aggregate metrics. There's been a lot of work on kind of opening the black box and interpreting deep learning models, but the most relevant to these are probably RNN-Viz by Manh et al., which looks to explain RNN on text and also allows users to compare the behavior between two, and then also CNN comparator, which compares multiple iterations of the same CNN model. But these are not architecture agnostic. They require either using an RNN or CNN. There's also been great work by Ren et al. Called Squares, which allows users to deeply explore classification results. But again, only works on, it is architecture agnostic, but only explores the results of one model without direct comparison. So in our work, I'll go over the formative interviews, how we designed it, our design goals, and then also do a short demo of the prototype. So for the formative interviews, we conducted 3 open-ended semi-structured interviews with 5 machine learning experts. Each session was 1 hour each, and the 3 sessions were divided based on application area. So in all cases, we asked the experts to talk about a model that they're currently working on or had recently worked on in the context of comparison. So the first 2 experts were working on text-based question answering using context. So if we want to ask a question about a product and all we have is this picture, say it's a water bottle, we have a picture of a water bottle and the user asks, how much water does it hold? We can get the answer 16 ounces. The second 2 experts were working on next action prediction using user behavior logs. So for example, if we have the history of pages a user visited, what's the next page they're likely to visit? And the last one was outcome prediction based on user profiles. So if we have, say, the demographics of a particular user, are they going to make a purchase or not? So across all these applications, we found that there's 3 main tasks they perform when doing comparison and 6 challenges associated with that. So the first was across the board, the first thing to do, obviously, is compare aggregate performance metrics. So this could be things like precision or recall, accuracy, or maybe a custom metric that takes into account weighing false positives or false negatives. And this is the best way to get a high-level overview of which models are worth maybe exploring more or continuing with, or whether your progress is increasing or decreasing. But the challenges here are that there's a loss of detail. So 2 models could have the same exact accuracy and wildly different performance, and then also a loss of context. So if they see, if say in the tuning case, if the user changed two parameters and there was a difference in the results, they can't necessarily go back and understand how exactly those changes affected the results. Second was being able to identify major misclassification patterns. So typically this is done with confusion matrices in classification, which is a great way to see the classification patterns for a single model, but didn't necessarily extend to two or more. So there's this lack of direct comparison between the two. They have to do this for each of the models individually. And then lastly, a lack of explanation. So if they discover that in a number classifier, for example, it's classifying 2s as 5s, they can't really go back and see why that happened. And then lastly, this leads to inspecting model behavior. So it's difficult to be able to compare between two different architectures and see how similar neurons are firing between, say, CNN and RNN. And then so understanding behavior at a neuron level or feature level is also difficult. So from these 6 challenges, we developed 6 design goals. They're explained more in the paper, but in the interest of time, I'll just go over 2 of them that will be helpful for the demo. So first was being able to provide a high-level overview of the classification patterns. So as I mentioned, they typically used confusion matrices for this, but that didn't extend well to 2 or more models. So what we did was create a hierarchy that could be generalizable to multiple classifications as well as 2 or more models. So first we take all the test instances, divide by the ground truth classifications, and then from there, for each of the models that we're comparing, do a binary split based on the correctness. So for comparing 2 binary classification problems, this would result in 8 categories, which we then visualize as a tree map. So in this particular one, you can see that so this one has 1,000 test instances, about half are negative and half are positive classes. And we can see that in both cases, the models are both getting the same proportion about correct, but the CNN is performing a bit better on negative classes, and the LSTM is performing a little better on positive. The second thing is being able to compare tests easily across the models directly. So for each test instance, we employ this pillbox design where the background color is the ground truth, and then we inlay rounded squares for the actual predictions for each model. So this could be extendable up to however much space there is on the screen for the models, but is limited by the color for classifications. And this also represents these kind of natural glyphs for the different classes as well. So when both models are correct, there's no contrast, but when there's models incorrect, you can see the contrast. So DeepCompare is comprised of 4 main panels. First, we have a representation of the learned weights in the trained model themselves. So we employ a heat map design so that it's flexible based on how the user wants to represent their neurons, since there's not really direct mapping between neuron layers and learned weights. So in this example, we're comparing a CNN to an LSTM performing movie review sentiment classification. And the CNN has about 300 neurons, which we can scroll, and the LSTM has about 150 with 2 outputs. So the first thing the user can do is explore specific neurons and their activation patterns. So by clicking specific activation patterns, we can see a distribution summary of the activations. And if we click around, we can see that the activation patterns are quite different between the models and also within the models. So if we select, say, neuron 0, the second thing is also we have a detailed view of the test results. So for each instance, there's a row. And then we have the pillbox design showing the results in view. So what we can see is if we select neuron 0, these are sorted by the activation for that specific neuron now. And we can see that there's a lot of Spanish language reviews coming to the top that this neuron maybe is capturing. And if we look at the results, we can see that the CNN is performing better on these results than the LSTM. It's getting it incorrect more often. This was one of the examples from the machine learning practitioners, and he was surprised at this because he didn't even realize that there was Spanish in the test or training sets. So that was a surprise. And then the last thing is being able to use that same test result summary to see specific classes. And we can dig down into specific classes. So if we want to see exactly the class or the instances where the CNN is correct and the LST is incorrect, we can filter by that and then also get a summary view of the words that appear in that. So of course this work is not without limitations. We only tried this with text data, so we do have to see how to generalize to non-text data types such as images or tabular data. Also, there's issues of the scalability of the heat map and our use of colors. So the models that we use were quite small with only hundreds of neurons, but there is obviously commonly thousands, and so we'd have to see how that would scale. And we've only performed a couple of preliminary case studies. In future work, we'd want to see how we could automate some of the insights on the similarities and differences in performance, particularly being able to automatically correlate neurons and features between the models. So if we have the two different architectures, how can we correlate the models or the neurons to show similar features between them? And we're also interested in incorporating training data to understand how the models learn and to be able to identify gaps. And that's all I have, so I'll take questions now. Thank you.